Okay, so my microphone on my computer wasn't working, so I'm just going to use my phone to try to record this and help you out a little bit. Number one, so it says the passenger feels that we weigh, or that she weighs 500 newtons. So the fact that that word feels there means that that's the normal force. How you perceive your weight is the normal force. So we know N equals 500. Explain which force provides, okay, well, that's the normal force. How fast means we're going to be looking for the speed, and it says draw a quantitative force diagram. So my force diagram is over here. I didn't put numbers with it, but I know that the normal force is 500, and I know that I can find my force of gravity by doing 60 times 9.8, and that equals 588. So I could have drawn a quantitative force diagram here. We're looking for the speed, though. Now, the force of gravity here at point A is going to be center seeking, and the normal force is my center leaving force. So I have Fg minus N equals mv squared over r for my centripetal force. So 60 times 9.8 minus 500 equals 60 times v squared over 3. Now, if you do the math, so you want to simplify 60, you want to subtract this first, and then multiply both sides by 3, divide by 60, and then take the square root. When you do all of that, you'll get a speed of about 2.1 meters per second. That's how fast you have to go to make that loop. All right, on number 2, it's the same idea. We're looking at point B. Now, at point B, the normal force has to be greater in order to make that circle, because my center seeking force has to be larger, so my centripetal force is going to be N minus G. So, let's see. It says the rider will experience a normal force of 5 times their weight. Well, if the weight is 900 newtons, then the rider is going to experience 5 Gs, or 5 times the weight, which is 4,900 newtons. You can just do 5 times 980, and you'll get the normal force. So, then we have the normal force minus the force of gravity equals mv squared over r. Do this algebra, and you'll get a radius of 12 meters. Number 3, so this is the side of the loop. So we have the normal force pointing to the left and the force of gravity pointing straight down. Now, in this case, the force of gravity is neither center seeking nor is it center leaving. There's no component there, so it has nothing to do with the centripetal force. So the only force that is my centripetal force is the normal force. So we have N equals mv squared over r. I'm given the mass, the speed, and the radius. Just plug those in, and you can get a normal force of 4,000 newtons. All right, number 4. 4 is where we're upside down. So how fast is asking us to find a speed. We're given a radius and 200 Newton downward normal force. That's because the seat is pushing down on the kid when you go upside down in that curve. So my centripetal force is going to be N plus Fg, and you set that equal to mv squared over r. Plug in everything you know, and you can solve for v to be 7.7 meters per second. Number 5 really doesn't have a good question associated with it. I should have asked you to, find the speed or something, but really I only asked you for a quantitative diagram. Now it says that the roller coaster exerts a downward normal force on the track of 90,000. All that tells you is that the track then is going to exert an upward normal force on the roller coaster equal to 90,000. And then you find your weight the same way you always do. So 2,000 times 9.8 will give you 19,600. Alrighty, number 6. I know I'm going fast. I'm sorry. Doing this on my phone is no fun. At the top of the hill, okay, we have a 5 meter radius. We're moving at 6 meters per second. Draw a quantitative force diagram. How many G's would any passenger feel? So it's asking us to find the normal force because it's asking about how we feel. So the force of gravity is determined by 9.8. So that's going to be 5.88 times, let me back up. That's going to be 60 kilograms times 9.8 to get 5.8. Oh, good grief, 588. And because this is going over the hill like this, the force of gravity is my center seeking force. So we have force of gravity minus the normal force this time, minus my center leaving force, equals mv squared over r. And so 60 times 9.8, that's where I got the 588, minus n equals my mass of 60, that's given, times the speed of 6, that's given, over a radius of 5. Once you solve for n, you get 156 newtons. Now that is the force. The problem is asking us how many g's. So the number of g's is given by the normal force, how you feel, divided by your usual force of gravity. So I took 156 newtons and divided that by 588, and you get about 0.27 g's. So you feel a lot less than normal. All right, now number 7. So this one, it seems complicated at first, but if we just simplify a few things, then it's super easy. So a car travels over a hill at a constant speed if the radius is 30 meters. At what speed would the centripetal force equal the force of gravity? Guys, it tells you Fc equals Fg. This is that moment where the normal force is 0. So any faster and you're going to be airborne, basically, okay? It's like that moment where you feel like you're coming up out of your seat in the car. So I set up Fc equals Fg. Well, we know the equation for centripetal force is mv squared over r. Anytime you're not given a variable, just write out the equations without any numbers and then see if that variable will cancel, because in this case we didn't have mass. But I knew that Fg, the weight, could be represented by little m times lowercase g, or 9.8. Then it becomes a pretty simple equation to solve for v. You do 30 times 9.8 and take the square root to get 17. And then it says if the car were to exceed this speed, what would happen? Well, you're going to be airborne at that moment. Oh goodness, I don't want to change things. I'll just back up a little bit. All right, number 8. So, using the principles of circular motion to find the centripetal force, that means we're going to use mv squared over r. And you can see all I've done, guys, is really just plug stuff in. Little m in the equation represents the mass of what is moving in a circle. So in this case, that would be the shuttle mass, not the Earth's mass. And of course, we're given the speed or the tangential velocity of the shuttle, 7,823. And then the r in this case represents the orbital radius. So we have to add the radius of the Earth and the altitude of the shuttle. And we plug all those numbers in and very carefully use our calculator, and we get that the centripetal force is about 72,000. When we look at Part B, it says use the law of universal gravitation. Well, that's the g m1 m2 over r squared. So again, you just plug in values, use your orbital radius and square it, and you'll get a force of gravity of about 856,000. Now, those are not the same, but my goodness, they are awful close when you look at the grand scheme of things. Actually, if we were to compare those two numbers, like we need to in Part C, you would find that those numbers are only 2% different. So, what that means is, if we want a perfect circular orbit where the force of gravity is truly the force needed to go in a circle, then maybe this shuttle is actually moving a little too fast. Okay, so that just tells us that maybe this orbit isn't perfectly circular. There are other forces in play, like the gravity that it's experiencing or feeling from the moon or other planets, or the sun. All of this could be reasons why these are off a little bit, but for the most part, they are the same. And this just shows you that when you're in orbit, the centripetal force is equal to the force of gravity. I know this was really quick, and I hope it helps you prepare for your test just a little bit. Please text me if you have any questions.